Hi everyone, I'm Jorge Osuna and I'm going to present the paper with the name Adaptable Onboard Computer for Nanosatellites. The authors of this paper are Braulio Peraza, Eduardo Ángel, Jorge Osuna, Luis Rizo, Mario Bárcenas, and Rafael Prieto. Okay. During this presentation, we will cover introduction, platform design, concept of architecture, implementation design, integration and testing, and finally, conclusion. For introducing this topic, we can start talking about nanosatellites, which are characterized by faster development times and lower cost compared to bigger satellites. These characteristics provide an opportunity for academic and private sectors to test their new ideas for applied technology. This includes some universities that are currently validating suborbital designs. There are some Mexican universities that are investing efforts to develop this kind of technology. One of them is ITESO, which is collaborating with other two Mexican universities to develop its first nanosatellite. One of the main components of nanosatellite is the onboard computer, which is the main controller of the device. It handles data between other subsystems and hosts the payload. Although the use of reconfigurable technology for onboard computers is not a new topic in nanosatellite development, there are new proposals that look to exploit the adaptability of this type of technology in different ways. The scope of this paper is focused on the design of an onboard computer with reprogrammable technology that can be adapted to several subsystems throughout the development cycle of a nanosatellite. For that approach, we selected the SYNC, which is a system on chip that has both microcontroller and FPGA embedded into a single SoC. To design the onboard computer, we use the PC104 template that provides an electrical and mechanical standard for PCB creation. This standard is mostly used by CubeSat community. The onboard computer architecture is based on commercial electronic components which are often used for aerospace prototypes. Therefore, they have a cheaper design cost and validation tests are faster. In order to complete hardware and software specifications, a core board unit XME0724 was selected to be integrated in the PCB. The main element of that unit is a Sync 7000 processor. In this slide, we can find the PCB design, which complies with the PC104 standard dimensions. In this slide, we can observe the diagram for the implementation of the XME0724 module and the architecture sync distribution, which is shown here. Then we have two principal voltages were distributed to the PC104 connector. One has the 3.3 volts and the other has the 5 volts. The processing system incorporates the external SD storage, which is over this micro SD, and also for communication it has these peripherals for CAN buses, which is the 0 and the 1, and also it has the UART interface. Then we go to the PL, which is the programmable logic, and it includes an FPGA interface with the JTAG, which is shown here, and also it has the I2C bus, which is here, and also the 20 GPIOs, which are wired directly to a PC104 connector. In order to validate onboard computer communication over I2C bus and data storage, a second PCB was designed. That is called payload, and it contains sensors to read environmental data. Sensors are shown in this table. These devices send some environmental data to the onboard computer that includes air quality, pressure sensor, real-time clock, and other information related to position or location. This implementation, being a co-designed, was a little bit different from classical software-only approach. For co-designed, we consider both of the reconfigurable internal hardware that has to be programmed into the FPGA and the software application that will be programmed into the microcontroller. Then the development is split into these two mentioned phases. For the FPGA hardware configurations, the Vivado Suite design provided by Xilinx was used. With this tool, the hardware details are set with a user-friendly interface. Once the FPGA was programmed, the software development was started. The software program periodically monitors the sensors, as shown in this diagram. Sensor readings are obtained sequentially over I2C communication. Once the 4 sensors are read, the program saves the data of the current readings in memory. In case the memory is full, the oldest data begins to be overwritten. After the data is saved, the loop starts all over again and will continue until the device is powered off. At the end of the mission, data can be collected from the memory to update all the sensed data. The developed onboard computer and its payload were assembled using plug-and-play scheme because it is meant to be compatible with an assembly that bundles other boards together. The compatibility with other models can be observed in the left picture. Here we can see there are different boards, different than our project. The assembled system was sent to a laboratory of other Mexican university called UNAM to be part of a more complex project called EMITS-3, which is a scientific technological platform to evaluate aerospace prototyping. It has a PC-104 module adapted to add external units. In the picture of the right side, we can observe the assigned position for our onboard computer and payload. And we can see here that our boards are integrated inside of this tiny place. For the testing, there was a hardware configuration test, which validates that the I2C driver can be mapped to different pins over the extended multiplexed inputs-outputs. This implementation can be observed in the case 1 shown in the diagram, which should handle I2C communication properly. Afterwards, the pin package configuration was modified and reprogrammed to the FPGA to obtain case 2, shown in the diagram. After every change of the pin package configuration, the design must be rebuilt and the software reflashed to have the new changes in the sync. The result of the test was that both configurations worked properly using different pins. Other test was the vibration test. It was performed on the EMITS in the Aerospace Test Integration Laboratory from Mexican University called IPN. That was composed by 2 mechanical tests. The first was the random vibration test, which confirmed that EMIT's integration structure was free of defects. The second test was the sign vibration, which confirmed that the EMIST integration structure is able to resist a low frequency launch environment. Normally it is between 5 and 100 Hz. After performing this test, we concluded that the OBC, which is the onboard computer, and the payload was capable to withstand the vibration conditions from a real launch scenario. Okay, then for the conclusion. The development of this subsystem has been challenging, as it incurred in longer design time due to an increased complexity in terms of architecture compared against usage of application-specific integrated circuits. Nonetheless, the versatility it provides can easily compensate for its cons, as it allows to avoid PCB redesign when incompatibilities between subsystems are found, which is especially useful when it's used for multiple subsystems validation. For the future work, the team is currently waiting for the data gathered in the flight performed on NASA's FY22 Fort Summer campaign, which will provide feedback on the onboard computer performance and reliability. This onboard computer will provide design flexibility for future subsystems of ITESO's nanosatellite. The limitations of the board adaptability will be put to test in the next design iterations. This has been the article overview presentation. Thanks a lot, and feel free to ask any question.